Dear colleagues, dear friends, thanks from myself and Violeta, and myself, for your participation in this wonderful, successful colloquium of Science Meets Art, or Arts Meets Science, of our Academy. Tonight, this evening, we have two leading figures, truly interdisciplinary scientists, and both of them touch entirely on the arts and science content, the coupling of our colloquium, from maths to philosophy, from physics to psychology, from medicine to computer sciences, and to art. I'm eager to learn from these two important, significant presentations, and time runs, and so I would like to ask Violeta. But before I would like to ask two assistants whose support is valuable. One is Doris from the office of East Salzburg, and the other is Mitchell from technical support. So you would like to say hello, Doris, Lida?
Hello, good evening. Hello. On behalf of the European Academy of Science and Arts, I would like to welcome to the colloquium as well and wish you a wonderful, scientifically inspiring evening.
Thank you, Lida. Mitch, can you say a few words?
Yeah, thank you. I appreciate that. Thank you for mentioning. I'm sitting here in north of Hamburg, and I would also like to inform you about two things. So please mute your microphone during the presentation. You are welcome to activate your microphone during the discussion afterwards. And I also would like to mention, or I also need to inform you about the recording and subsequent publication of the meeting. If you do not agree, you should not activate your microphone during the recording. Thank you.
Thank you, Mitch. Violeta.
Thank you very much, and I agree. So I'm happy to be here again. And I have the pleasure to introduce our first speaker. He is also our president of the European Academy. Klaus Mainzer, philosopher of science, studies the foundations and future perspectives of science and technology. He focuses on mathematics, basics, research, and computer modeling of science and technology. He is known as a researcher of complexity with a focus on complex systems, algorithms, and artificial intelligence in science and society. Mainzer studied mathematics, physics, and philosophy. He obtained a doctorate in philosophy and mathematics fundamentals, mathematical constructivism. In 1979, Mainzer got his habilitation in philosophy with a thesis on space, geometry, and continuum at the University of Münster. He received also a Heisenberg grant. He was a professor for the basic theory and history of exact sciences at the University of Constance and the vice-rector of the University of Constance. I have so many information about him. He is the founding director of the Interdisciplinary Institute for Computer Science at the University of Augsburg. He held the chair for philosophy and philosophy of science at the Technical University of Munich. He was appointed director of the Carl von Linde Academy. He was the Munich Center for Technology and Society founding director at the Technical University of Munich. And he has been Emeritus of Excellence since 2019. He has been senior professor at the Faculty of Mathematics and Natural Sciences and the Tübingen Center for Advanced Studies at the Eberhard Karls University of Tübingen. I follow essentially this wonderful biography. He gave guest lectures or carried out visiting professorship in Brazil, China, India, Japan, South Korea, America, and Russia. He was a visiting scientist at the Other University in International Mathematical Institute in St. Petersburg. Klaus Mainzer initially published on the concept of a number, the fundamentals of geometry, space, time, symmetry, and quantum mechanics. He became known as a fundamental theorist of complex systems and artificial intelligence. He was the first who examined mathematical models of complex systems that organize themselves in nature. In basic mathematical research, he began studying constructive mathematics against the background of Kant's philosophy. Based on degrees of predictability and constructiveness, he researched the extent to which mathematical proofs and thus human thinking can be reduced to algorithms and computers. The world's calculation leads again to complex systems and the question of the degree to which they can be digitized. In November 2020, the European Academy of Sciences and Arts elected Mainzer as its new president. He succeeded Felix Unger, who had served as president for 3 decades. Please, I would like to invite now Klaus Mainzer.
Oh, thank you very much. It was excellent, but I think too long. And thank you so much. And welcome again to our lecture series on the science and arts meets science. And the topics this evening is actually in the center of both, namely science and arts, symmetry and symmetry breaking in science and arts. And the background is my lifelong studies in this field. For example, here on the right, the book Symmetries of Nature, published for the first one in 1988, and then a second one in 2005, Symmetry and Complexity. And the message of these studies, I think, is very easily to understand. Namely, in the beginning, there was symmetry and simplicity, but the emergence of variety, of complexity and novelties is only possible by symmetry breaking. And so I start with some remarks on symmetry and symmetry breaking in early science and arts, and I will consider the concept of symmetry from a modern mathematical point of view, then symmetry and symmetry breaking in the universe, in the molecular world, in life, and finally in modern painting and music. Now let's start with symmetry and symmetry breaking in early science and arts. And I like to start with the early high cultures of mankind. Here at first, symmetries of Indian cosmology. And here in the center, you see regular triangles as symbols of divinity and surrounded by spheres with fire, and then the spheres of being. And all that is in a rotational circular movement in an eternal way. That's the belief of the old Indians. Now, China, of course, one of the great old cultures here with the assumed elements of nature in that time, sky, sea, fire, thunder, and so on. And it's remarkable it is represented here by a bit code. In the I Ching, that means unbroken and broken lines, here as trigrams, and all these elements are ordered in a rotational symmetry here on the surface of an old Chinese coin. And then Europe. Europe, of course, started in Greece, and the symmetry and harmony of Greek cosmology. Plato's cosmos is a centrally symmetrically ordered system with the Earth in the center and surrounded by spheres. And the spheres are fixed, the belief, the assumed planets in those days. And according to the Platonic Pythagorean conception, the motion of each one produces a sound, so that the tones of the movements of the spheres jointly form harmony of the spheres in the sense of a well-ordered musical scale, like the strings of a lyre. And these early ideas were later on in the following cultures repeated, for example, here in Christianity, the symmetries of Gothic, here a rose window at the Cathedral of Strasbourg. And that was a belief in the Christian Middle Ages, namely the harmony between scientific knowledge and religious belief. And the same ideas in the Jewish and Islamic tradition. For example, here, the central symmetry of the dome of Al-Kaaba in Seville, 14th century. And you know, in these cultures, in the Jewish tradition and in the Islamic tradition, it's forbidden to represent divinity by human persons. And so they use perfect mathematical symmetry of ornaments. And here is an example of the Greek tradition to illustrate harmony, the proportionality of the golden section. This is a famous proof by Euclid. I will not go into the details. The ethical effect of the golden section is explained, that is the idea, by harmonizing unequal parts. And that is illustrated here in the proportions and the harmony of antique architecture. Here's a construction of golden sections for the Parthenon in Athens, or the canon of proportions in Polyclete, 440 before Christ. And this old Greek term logos nowadays in philosophy means reason, but actually it is a technical term coming from Greek mathematics and means proportionality. One can say, in short, the Greek antique mathematics means a theory of proportionality. Here also, for a famous antique statue, here the golden sections. Now, symmetry breaking. You remember symmetry in Plato's universe means spherical symmetry with the Earth in the center, and the planets are fixed on the rotating sphere. And that is the position of the observer. And so it cannot be explained from this point of view, the actually empirically observed retrograde movements. For example, here of the Mars, and Plato was horrified by that, and he asked his mathematicians, how can we save the symmetry of heaven by uniform circular movement? That was the paradigm. And one of these suggestions was made by Apollonius of Perga, and he suggested the construction with epicycles and difference. And that means we start with a planet moving on a little sphere, assumed sphere, the epicycle, and the center of the epicycle is moving uniformly around the center here, namely the Earth, and the combination of both uniform circular movements generate these figures here, these slopes, these retrograde movements, which, by the way, also explain the changing light by the changing distance of the planet to the observer. But in later times, until the late Middle Ages, a lot of deviations from the assumed Platonic circular harmony were observed, and so the astronomers were enforced to introduce epicycles of epicycles of epicycles. It was a variety, highly complicated, mathematically completely exact, in order to generate all kind of observed movements, here the trajectories, but actually it could not be explained by physical reasons, even not in the tradition of Aristotelian physics. Now that was the macrocosmos. Now the microcosmos, and here again in the Platonic tradition, people were convinced of symmetry principles in nature, and it was well known in those days that according to Euclid's fifth book, there are only exactly 5 regular bodies in the Euclidean space. These are the tetrahedron with 4 regular triangles, and the octahedron with 8 regular triangles as element, the icosahedron with 20 regular triangles. And you see, in this case, these elements can be combined among another kind of Platonic chemistry, but that is no longer possible here for the 4th and 5th element, namely the cube consisting of 6 regular squares, and the dodecahedron consisting of 12 regular pentagons. And Plato believed, and that was of course a speculation in those days too, that these distinguished mathematical regular bodies can be identified with the assumed elements of nature in that time, that was fire, air, water, earth, and the building blocks of the celestial spheres. But anyone that was a strong belief in symmetry, even in the microcosmos, very influential in later time, this belief was shared even in Renaissance at the beginning of modern time. For example, here Johannes Kepler, the famous mathematician and astronomer, he at first believed that even the heliocentric system of planets can be distinguished by Platonic symmetries. He tried to determine the distance of the spheres of the planets here around the sun by inscribed embedded Platonic figures, but later on that was falsified, and Kepler gave up this early speculation. But he believed, and that was very modern, in the symmetry, he said, of mathematical forms. Not only the forms, and that is very, very essential for the following, not only symmetries of geometrical visible figures and bodies, but the invariants, the unchangeable forms of mathematical laws, namely of here in this case natural laws. This is of course a famous symbol of those days in Renaissance, the mirror symmetry of Leonardo world. And you know, Leonardo is one of our heroes in this lecture series. Now the concept of symmetry from a modern point of view. That is also very easily to understand, but it is a little bit abstract. The symmetry of a set in general, that may be a set of points, numbers, functions, whatsoever, is defined by the group of self-mappings. That is called automorphisms, that leaves unchanged the structure of the set after application. That means invariance of proportional relations in Euclidean space that may be arithmetical rules of numbers whatsoever. And there are only 3 very simple requests. First, the identity is such a self-mapping. That means the identity that maps every element of a set onto itself. And for every self-mapping, the automorphism, there is an inverse, backward self-mapping, bringing us back to the origin. That means identity, and the successive application of self-mappings is again a self-mapping. That is all. And all these examples which I showed you before fulfill these simple axioms. For example, here, mirror symmetry. Here, the inverse element is the self-mapping itself. Or similarities here of triangles. That means invariant, unchanged after application of the self-mapping is the form here, not the size. The size here is the change, but in the case of the so-called congruences, then also the size is unchanged, and here a mirror symmetry is also considered. And then by these elements, exactly all kinds of symmetries can be reconstructed. For example, frieze ornaments. That means ornaments in one dimension. Here on the left, these are these kind of self-mappings, namely here translational symmetry. That means shifting the same ornament. Here it is combined with horizontal symmetry. That means mirror symmetry here on the horizontal axis is an example of arts. And here we have also vertical mirror symmetries. This is an example, inverse symmetries. And here the combination of all these elements with examples in arts. So in the end, in this case, exactly there are seven kinds of these symmetries, frieze symmetries. And then that was one dimension, 2 dimensions, a plane. And here exactly you can prove there are 17 possible symmetries. Or invariance of forms, unchangeable after application of these self-mappings. That is also rotational symmetry. For example, here these polygons, regular polygons, after rotating with respect to a certain angle, then the whole figure is unchanged clockwise. And combined here with bilateral, that means mirror symmetry, you get the full symmetry group of this figure. And if the angles are infinitesimal small, then you get the continuous symmetries, for example, for circles, spheres, and so on. And here we have symmetry groups which describe the Platonic bodies. There's one symmetry group which describe the octahedron as well as the cube. That means, again, by the allowed rotations and bilateral or mirror symmetries. Now, on that background, we can now understand the modern applications. But we must remember the main insight which you already had, Johannes Kepler, namely that symmetry, this kind of invariance of form, that is the basic idea, invariance of form. Form is not only restricted to geometrical figures and bodies, but also to the form of any kind of structure. That means to the form of laws, natural laws, mathematical laws. And now the first highlight was in the beginning of the 20th century, the insight that the symmetries of space and time imply the famous conservation law, fundamental laws of physics. That was, by the way, proven by one of the great women mathematicians in the last century, Emmy Noether, and spatial translation, spatial rotation, time translation. That means here the law, the physical law, is invariant, does not change. The equation does not change after application of shifting in time. That means time translation. And that implies, that's easily to prove, the conservation of energy. But now I think a highlight is, of course, until nowadays, the modern cosmology. And here, modern cosmology is inspired by Platonic ideas, the so-called standard theory. The main difference is that it is not restricted to a static universe, like in the Platonic tradition, but to an expanding universe. So that means this model, the standard model, assumes that in the beginning there was a unified force, and that this unified force was is described by mathematical laws which are characterized by symmetry, actually symmetry groups in the way which I mentioned before. Now, during cosmic expansion and the cooling temperature, that is illustrated here, the energy axis, the temperature axis, the time axis, the originally unified force characterized by a unified symmetry broke apart step by step into subsymmetries of new physical interaction. That means all these well-known forces now, gravitation, strong interactions and nuclear forces, weak interaction, electromagnetic actuation, were separated step by step at certain critical points of temperature, of energy. And by that, we get these partial symmetries and the emergence of new variety of elementary particle, new kinds of particle emerge, which are typical for these new interaction, which I mentioned before. And that was made possible by symmetry breaking process, spontaneous symmetry breaking, the famous Higgs mechanism, which is well confirmed nowadays empirically too. And the roughly speaking, the idea is that originally massless fields, particles or fields of interaction particles become spontaneously massive and distinguishable in order to characterize these new kinds of particles. And this step here of the bifurcation tree, these steps are established physics today, theoretical physics, empirical physics. That means that we are already able to reconstruct these early stages of the universe, of these unified stages of the interaction here by very high temperature and energies. And so far, it is also called high energy physics. Now, this is the mathematical side. These are the well-known interaction which I mentioned: gravitation, strong, weak, and electromagnetic interaction, characterized by these symmetry groups. I cannot go here in the mathematical details. These are the earlier stage of unification with the corresponding, of course, greater, larger symmetry groups. And that here is well established, not only mathematics, but also physics. But the last step, that is, of course, one can say mathematical metaphysics. That is an hypothesis now. The difficulty is these kind of interaction are described nowadays by quantum physics, and gravitation is described by Einstein's general physics, and that is, of course, a great difficulty, classical and quantum physics, to be unified. Anyway, we have some nice mathematical theories to describe this early stage. One is superstring theory, which I like to mention because of its aesthetical aspects. The belief, the assumption here is that there are a substructure of matter below the elementary particles of the standard theory, the so-called strings. These are chords or closed loops, and according to relativity theory, their oscillating patterns generate energy and mass of elementary particles. So, and that has a nice analogy with the strings, for example, of a violin generating tones of music, such as a lyre in antique cosmology, which I mentioned before. Now let's climb up from the elementary particles to the molecular world. And here you all know these nice symmetries of macroscopic crystals, left-handed and right-handed quartz here. But these kinds of symmetries are actually caused on the molecular level. And that can be proven in water-soluble crystals. For example, tartaric acid, this is shown here, the chemical formulas, and even a layman can see these nice symmetries, the bilateral symmetries, a mirror symmetry here in the case of left-handed and right-handed tartaric acid, or in the case of mesotartaric acids. These are the three possibilities. If in the soluble case with the mirror symmetry along this axis, or the symmetry of fullerenes, which is well known with these big molecules, which inspired Buckminster Fuller, famous US architect, to use it, even this structure, even in architecture. Or here in supramolecular symmetry, chemistry nowadays, these huge molecules are constructed artificial for very practical applications, namely as a kind of container for chemical substances of medicaments in the blood vessels. And here the huge symmetric modules, which often consist of smaller molecular units, and which obviously have the structure of regular polyhedrons. And this kind of Platonic structure is actually confirmed in the molecular world. But of course, the molecules are not colored in these nice colors. But now, symmetry breaking, not only in modern cosmology, but symmetry breaking in life science. In the amino acids, that means the building block of proteins, and by that, the building blocks of life. Protein analysis show amino acids here, which have an antisymmetrical carbon atom here with mirror symmetry here in the center, and occur only in nature in one version, only in the left-handed configuration, not vice versa. So molecular antisymmetry seems to be typical for life. This is another famous example. The DNA spirals are always turning right. The distinction of a direction guarantees uniqueness, that is a function Y. Correctness of DNA codes for replication as foundation of life. And that reminds me of a famous speculation of Louis Pasteur, one of the founder of modern life sciences, at the end of the 19th century. And he already speculates that asymmetry, he says, is typical for life. And that has a nice relation, by the way, to literature. There is a famous quotation in the novel of Thomas Mann, Zauberberg, The Magic Mountain, and one of the main actors there is Castorp, and Castorp during a snow storm is considering the crystal of a snowflake. And then he said, life shuddered with cold symmetry. Symmetry means death. And that brings us to symmetry and symmetry breaking of life. Here, this is a bifurcation tree again. It started with a cosmic bifurcation tree. Symmetry breaking is here. I mentioned that, explained by the Higgs mechanisms in physics. Then the next step is a chemical evolution with the symmetry breaking of equilibrium states in thermodynamics up to the bifurcation tree of life, the famous Darwinian tree. And here again, these bifurcation points in this case are explained by biological symmetry breaking, namely the random mutations leading to these driving forces here in the branches with the emergence of new organisms. And the organisms must be adapted to the environment, you know, and that leads to the emergence of new functional symmetries. For example, here, the mirror symmetries for these butterflies or birds, for flying in the air, or here for swimming in water, or here for walking on the earth. And bilateral symmetry of nervous system is a dominating principle of evolution of mammals, but here in the case of the human brain with local deviations. That means local asymmetries which are caused by the emergence of new functions of in information processing in the later stages of evolution. But not only symmetry and symmetry breaking in organic systems, but also in the human mind. Cognitive symmetry breaking, a source of creativity. Do we see a vase or a face? Actually, it depends on tiny, more or less random awareness of details, first details, and this kind of spontaneous symmetry breaking is illustrated here in this potential field, the ball representing the state of the system, and it depends on tiny fluctuation. That is a tiny awareness here, where the ball will roll in the left or the right valley, representing the emergence of a new structure, in this case, in this sense, source of creativity. By the way, that can also be done nowadays, not only with biological brains and mind, but also with artificial brains here, namely so-called neural networks in artificial intelligence, but I will not go here into details. So in the end, the question arises, symmetry, is that only a concept of human mind to reduce complexity, to order the variety in the world, or is it actually a physical structure independent of human mind? I think it is both. Symmetries of theories and models open insights into invariant structures of the world, but without symmetry breaking, there would be no novelty, no change, no news. Symmetry breaking opens insight into the variety and the complexity of the world. Now, some last remarks on symmetry breaking in modern painting. In modern painting and music, I already told a lot about old and former arts. Here, I like Paul Klee. He was also a philosopher in the first part of the last century. Broken symmetries in modern painting. Originally, here in that picture, there is the symmetry of a lattice, but here, obviously, with local symmetry breaking. That is also true here in this picture of him, this pattern formation. the local symmetries here seem to be soluble in this medium. Klee was not only, you know, a painter, but also a musician. And so he tried as a painter to explain even the fourth dimension, not only the three spatial dimensions, the fourth dimension of time. Here, the development in music in time with the repeating figures in his picture, Fugue in red, and that is also realized here in this tapestry of Klee. The parallel three tapes here remind us of the structure of a fugue in music. And that is now music itself. Two examples, one of classical music here, this ornamental symmetry in Beethoven's Waldstein sonate, and this is exactly the structure of the frieze ornaments, remember, which I explained in the beginning here with the vertical symmetry or the vertical mirror symmetry along the vertical axis, then symmetry along the horizontal axis, and translational symmetry by shifting. Here only horizontal mirror symmetry and translational symmetry by shifting, and here only translational symmetry. And then an example of modern music, Schoenberg's 12-tone music, of course, and he is strictly oriented to mathematical construction rules, starting with a normal form here by reflection at the horizontal line, vertical, retrograde, and the combination of both reflections. But in the end, this kind of construction leads to a complete break with traditional harmony. And Schoenberg called it emancipation of dissonance as the source of creativity, and that means symmetry breaking. Now, this is my last picture, M.C. Escher, Symmetry and Symmetry Breaking. He called it metamorphosis. And I think it nicely illustrates the ideas of this talk, namely the evolution of new structures by symmetry and symmetry breaking. Here, first with these crystal structures, and then the emergence of organic figures, finally the emergence of animals and any kinds of organisms, and in the end here leading to the emergence of urban structures of human civilization. And here in the end, it seems to be that the whole process is repeated in a kind of internal circulation. And that reminds me, or brings us back to the beginning of my talk with my remarks on Indian cosmology. I thank you for your attention.
Thank you very much. It is like a thema con variazione ad infinitum. It's wonderful. Thank you very much. And please, Ioannis, can you present the second?
Yes. Thank you, Klaus, for the very intriguing lecture. I hope, personally, I have actually several questions, but the questions will be, as we know, at the end. So now it is an honor for me to have with us Professor Thanasis Fokas, and I feel privileged to have to introduce Thanasis to you. Last time, I think it was during end of 90s, beginning of 2000, I had the opportunity to talk about his multifaceted work. It was at the awarding ceremony, I think, of the honorary citizen of the city of Delphi. Correct. Thanasis Fokas is currently professor and holds the chair of Nonlinear Mathematical Science at the University of Cambridge in the Department of Applied Mathematics and Theoretical Physics, and also is adjunct professor of Civil and Environmental Engineering Practice and Biomedical Engineering in the University of Southern California. He's a member of the Academy of Athens, Greece, and a new member of Class 4 of our academy, and as Dean of Class 4, I'm most happy to welcome him and wish you, Thanasis, all the best, especially health, power, creativity, and always internal peace. With a BSc in aeronautics, from the Imperial College, London, a PhD in applied mathematics from the California Institute of Technology, and a medical doctorate from the University of Miami, Professor Fokas in 1986, at the age of 33, was appointed professor and chairman at the Department of Mathematics and Computer Sciences of Clarkson University in the USA, and then to a chair of applied mathematics at the Imperial College in the UK, and followed the newly inaugurated chair in nonlinear mathematical science at the University of Cambridge. Thanasis has been awarded many honorary degrees and also from 5 universities and many awards. I will present you selected ones. For example, the Nonlinear Prize of the London Mathematical Society, the most prestigious prize in applied mathematics and theoretical physics in the UK. The last 5 earlier recipients, actually, of this Nonlinear Prize were Sir Roger Penrose, Sir Michael Burry, Sir John Ball, Kelly, and Hawking. The Aristion also Prize in Sciences of the Academy of Athens. This is the most prestigious prize of the Academy, given every 4 years to a single scholar of Greek origin, chosen from science, engineering, or medicine. And he was included in the New York's list of honors of the New Year's list of honors of the President of the Hellenic Republic, and he was presented with the decoration of the Commander of the Order of Phoenix, was selected also as a Guggenheim Fellow on the basis of stellar achievements and exceptionally promise for continued accomplishment. The ISI website of science includes Professor Fokas in the list of the most highly cited researchers in the field of mathematics, pure mathematics, applied mathematics, probability, and statistics. He serves in many and prestigious editorial and advisory boards, and he has written or edited a dozen of books and more than 300 papers. He is well known also for the Fokas method, his own method, taught in universities. It is an algorithmic procedure for analyzing boundary value problems for linear partial differential equations and for an important class of nonlinear partial differential equations belonging to the so-called integrable systems. The list is not exhaustive, but I have selected a few, as I said, major achievements of multi-scientific and interdisciplinary nature of our speaker. His current research interests range from fluid dynamics, fluid mechanics, complex analysis and generalizations, integrable nonlinear multidimensional partial differential equations, protein folding, medical imaging, and inverse problems, boundary value problems. Thanasis, the online platform is yours.
Thank you very much. Thank you. It is a great honor to address this distinguished audience, especially after the president. It's a pity I didn't know the content of the first talk, because if I did, I could organize my talk in such a way that in some sense it could be a dialogue with the president. But anyway, perhaps a couple of very brief remarks, because I was motivated by his very deep thoughts. One is this beautiful connection between symmetry, therefore aesthetics, and ethics. You see, the ancient Greeks, as you know, had this very important concept of kalon kagathon, which essentially means beautiful and ethical. And of course, as you know, Wittgenstein made this remarkable proclamation that ethics and aesthetics is one and the same thing. For a long time, I was puzzled by this statement. Not anymore. Another, perhaps, very clear illustration of the importance of symmetry, and in some sense, symmetry breaking, is that, as you may know, Copernicus makes the statement that because his orbits are elliptic, which therefore they have a deeper symmetry, that the spherical orbits, they must be correct. So, and last remark, I'm sure that the president knows that Karatheodori, my great ancestor, wrote a very interesting paper analyzing in some sense, symmetry breaking of the Parthenon columns. But there is a deeper relationship with what the president had to say in my talk, and this hopefully will become clear during my talk, because I know that people cannot concentrate for a long time. My talk will be short, so it will not be more than half an hour. So perhaps we will have more time for talks. May I share my screen?
Yeah, please.
Thank you. That's good.
Okay, now it's visible.
So is it visible? I hope it's okay. Yes.
Yeah.
Okay. You see, when I realized that my talk was only for half an hour, I decided to concentrate only on part of the talk. The original title included an representations, which I will not talk about. This is, in some sense, I believe, the second Big Bang in the mental evolution, but I will only concentrate on the first Big Bang, which essentially is the question of consciousness or awareness, whatever you want to call it. Since we spoke already about the ancient Greeks, as you know, they were the first essentially to start thinking deeply about the question of thinking. In that sense, in some sense, they provide the foundation of philosophical aspects of neuroscience. It is well known that they pose very deep questions, such as how we comprehend the well-known, if you like, difference between Aristotle and his great teacher, tabula rasa versus tabula inscripta, the importance of a priori knowledge. A great number of philosophers, including, of course, Immanuel Kant, Wittgenstein, address these questions, do have an advantage now. Do have an advantage towards a deeper understanding of these fundamental questions. My position is yes, and the reason for this is that these great minds lacked a major piece of information, namely neuroscience. And in my opinion, it is really impossible to answer this type of questions outside the framework of neuroscience. In some sense, this was first understood by Russell. See, Russell, this was the time when, you see, I have to move somehow because I cannot read I have to move the picture somehow because I cannot read my screen well. I apologize. Okay. So Russell wrote, this was the beginning of neuroscience, the first stages of neuroscience. So Russell wrote, a physical process starts from a visible object, moves to the eye, there changes into another physical process in the optic nerve, and finally produces some effects in the brain simultaneously with which we see the object from which the process started, the scene being something mental, totally different in character from the physical process which preceded and accompanying it. This view is so strange that metaphysicians have invented all sorts of theories designed to replace it with something less incredible. See, there are two remarks here. One is clearly Russell expresses his skepticism as to whether a pure philosophy without the help of science can answer this kind of questions. But the second aspect, which is even more interesting in my opinion, is that in a sense, this statement is not precise. is not precise. And this is not a criticism to the great philosopher. Who am I to criticize Russell? But just to emphasize even stronger his belief that it is really, I believe, impossible to answer these type of questions outside the field of neuroscience. So let us okay, so I will concentrate on visual perception, again, with the idea of emphasizing this connection with an inverse problem. So what is perception? Perception in general is achieved via deconstruction and reconstruction. In particular, in visual perception is achieved as follows. The recognition of a specific percept is achieved via the emission of light from the object, or more precisely, via the distribution of the constituents of the light, which, as you know, are the photons. As soon as the photons arrive at the retina, a complicated neural process is initiated that finally gives rise to the creation of the mental image of the object. This is the reason why Gerald Edelman, Nobel Prize in Medicine in 1972, writes, quote, "Every act of perception is an act of creation," end of the quote. You see, if you don't understand this process of deconstruction and reconstruction, this poetic statement of Edelman is meaningless. In my opinion, perhaps a more accurate statement would be that every act of perception is an act of reconstruction, or if you like, more precisely, is an act of the solution of an inverse problem. A useful paradigm for appreciating this suggestion is provided by the functional medical imaging technique called Spect, single photon emission computerized tomography. In what follows, I will discuss the employment of Spect for the reconstruction of this object, or if you like, of the reconstruction of the cut of this object. How is this reconstruction achieved? What you do is in the holes, in the tubes, you place some radio tracer, and through a complicated process of radioactive decay, which I don't have time to explain, finally photons are emitted from this object. These photons are captured by the machine and are they're stored in the form of a sinogram. So the sinogram is the data that you have as a result of the distribution of the emitted photons. And here is the mathematical inverse problem. Given this data, can one reconstruct this cut? And the answer is yes, and this is illustrated in this rough picture. You see, you can see the holes from which these photons were emitted. So this is achieved via purely mathematics. This is the only slides of my talk which will have equations. It's interesting because there's a long story behind it. You see, as I have worked for many years in medical imaging, and Spect, in some sense, is similar to PET. But the inverse problem associated with PET, due to some serendipity, namely in PET, positrons are emitted in two directions, opposite directions, and there are some cancellations. Therefore, the inverse problem is simplified. And in this case, one simply has to invert the Radon transform. So the inverse problem associated with PET is given the Radon transform, can you reconstruct the function? This is, as you know, exactly the same problem as it arises in computerized tomography, and this problem was solved by Radon in 1917. However, in Spect, this cancellation does not take place. So if you look at the first integral, if you didn't have the exponential, this is the definition of the Radon transform. So in this case, f hat of mu would be simply the Radon transform of the function f. Namely, the Radon transform is something very simple. If you like, the most natural thing you can imagine, you integrate a function along a line. But now, this is attenuated by this exponential which involves mu, and mu, actually, you have to find it by first doing CT, the X-ray attenuation coefficient. So the mathematical problem now, in order to solve the inverse problem associated with Spect, is given mu, a given f hat of mu. Can you reconstruct f? You see, this problem was open for many, many years. And actually, our co-author in medical imaging, Brian Hutton, was telling me that he was giving lectures, claiming that this would never be solved. But in the I had the great fortune and luck and honor to work many years with Israel Moiseyevich Gelfand, and together we introduced a new method for inverting integrals. And the first non-trivial application of this method was precisely the inversion of this integral. And the analytical formula is given by what you see in the next few transparencies, and my group in Athens has implemented this formula numerically, and this is how this picture was constructed. Okay, but what therefore we can say is that in this particular solution of the inverse problem, what we see is that from the knowledge of the distribution of emitted photons, mathematically, it is possible to reconstruct the object that emitted these photons. Therefore, it is natural to ask, when we see a percept, again, there is, our brain receives the distribution of photons. So could it be that the brain uses analogous computations for the creation of the mental image of this object? The answer is negative. For the reconstruction I just presented you, the computer follows very specific algorithmic steps. While for the reconstruction of a percept, the brain, in addition to utilizing the distribution of the emitted photons, relies crucially on prior information stored in appropriate neural circuits. This information, which is used in a highly dynamic way, has been created via earlier interactions with external or internal stimuli and has been stabilized via intricate processes involving memory. The precise mechanism which allows the brain to employ in a most efficient manner this prior information remains a mysterium tremendum. In summary, visual perception involves the process of deconstruction and the solution of a complicated inverse problem. The latter solution is achieved via unconscious neural computations, which immediately demonstrate the importance of unconscious processes. Taking into consideration the time involved in implementing the relevant reconstruction, it follows that awareness cannot be instantaneous. Hence, the statement of Bernard Russell that we see something mental simultaneously with the object which caused this neural image cannot be accurate. In the particular case of visual perception, awareness is preceded by, as I mentioned, by an unconscious process. I believe that this happens in every form of perception, and this leads to the first hypothesis, namely that every conscious experience is preceded by an unconscious phase. The mental representations of the constituents of a percept are constructed via the solution of different inverse problems. In visual perception, the solution of such inverse problems reconstructs, for example, the orientation, color, and motion of a given percept. These reconstructions are achieved by employing unconscious neural computations of local neural systems that are in different parts of the brain. So, mental image is what we actually see. Mental representations are the unconscious ingredients of this mental image. So, if a word, for example, is presented very briefly, the brain perceives it, but we are unaware of it. So this is called subliminal input, and this is what you see on the right side with the red, and therefore you see already localized areas of the brain, if you like, localized neural circuits in the brain solving these particular inverse problems. So the excitation in the brain is localized. However, if there is sufficient energy so that various different aspects of this percept are reconstructed, then you will see the activation on the other side. So if the presentation of the percept lasts for a sufficiently long time, then there will be a sufficient amount of incoming energy capable of exciting several of the local neural circuits associated with the elements of this percept. This gives rise to global activation and the creation of a mental image, together with awareness. So what is consciousness? Consciousness, or if you like, awareness, is the creation of a mental image which is generated following the global binding of the local neural circuits involved in the solution of the inverse problem associated with parts of a given percept. This idea that unconscious mechanisms are absolutely crucial for consciousness to emerge. If you like, in my opinion, there is, as a mathematician, as every mathematician, I value immensely the concept of continuity. The processes of unconscious and conscious processes form a continuum. The leading role in this continuum is played by the unconscious, and another illustration of this is what happens with emotions. You see, my colleague at USC, Antonio Damasio, is considered as the world expert in the interplay of emotions and feelings. So what are feelings? Feelings are the conscious versions of emotions. This distinction I made between unconscious perception and awareness is valid for everything, in my opinion. And for example, at the level of emotions, Damasio proposed to call the conscious form of emotions feelings. But this is quite more complicated. I don't want to go into details, but the unconscious phase is much broader than what Antonio calls feelings. You see, for example, if and there are details which I give in my book, Ways of Comprehending. And for example, when leptin decreases, then the brain understands that it has to create new energy. So how does it do it? Through two different mechanisms. One is it begins an unconscious process which finally gives rise to the feeling of hunger. So the feeling of hunger has an unconscious component whose neural basis now we understand quite well. But at the same time, the brain does something which never becomes, for which we never become aware. And this is, it takes steps necessary to decrease energy expenditure. This is another example of the interaction between unconscious and conscious processes and how the unconscious processes are really fundamental. I don't want to take more of my time, so I just want to perhaps make some connections now before I give you one more transparency and complete the talk of some of the statements that the president made. You see, the president emphasized the importance of emergence of complexity. And he emphasized one specific role through which complexity can emerge, and this is through symmetry breaking. Also, he emphasized a very beautiful relation between local and global processes. Namely, he spoke about the attempts of Apollonius to explain complicated structures via the epicycles. Here we see, therefore, how the interaction of local and global allows us to pass for simplicity to complexity. You see, these are extremely deep notions, in my opinion, and in order to comprehend, we have to make continuous use of these processes in the same way that the brain does. So in addition to emphasizing that unconscious and conscious processes form a continuum, I emphasize this mechanism that the brain uses, which are analogical thinking, generalization, abstraction, unification versus reduction, local versus global processes, and simplicity versus complexity, which I just mentioned. And since this beautiful series of talks provide the interaction between art and science, allow me to complete my talk by just emphasizing how this idea of local versus global and simplicity versus complexity, already emphasized in the earlier talk, appears in the work, in the beautiful paintings of Kandinsky. Vasily Kandinsky, by combining the basic local elements used by the brain in visual processing, and which are the local elements that the brain uses, lines, color, motion, he created marvelous global structures. Specifically, the line for Kandinsky no longer serves as outline of concrete figures, but has attained the freedom of an independent compositional element. Also, the role of any visual motif is now played by different forms of color. And finally, the importance of motion. Immobility in the works of Kandinsky is replaced by vortex-type motion. And here is one of his first abstract composition. Meticulous synthesis of simple elements can produce a highly complex composition. Indeed, zooming at any specific area, it becomes clear that the local building blocks are simply lines of various width, length, and texture surrounded by various forms of color. The synthesis of these simple local ingredients gives rise to a global composition of highly dynamic, through the role of motion, evocative complexity. Thank you very much.
Thank you, Thanasis, for this enlightening presentation. We move on to the discussions session now, and I would like to ask Violeta to start with questions for the first speaker.
Thank you so much. We had the pleasure to have two brilliant lectures today, and I'm sure we have already something in chat. Hervorragender Vortrag. Thank you very much for extraordinary lecture. Synopsis of the difference of but I would like to invite you for remarks or commentaries. please, you may also you may bring questions for both of them at the same time, because there is correspondences between your talks, because when we speak about consciousness and unconsciousness, it's also possible to understand symmetries, and breaking symmetries are anyway related to subconscious and conscious phenomena and processes.
There is a hands by Vesconyan. Okay.
Yes, do you hear me?
Yes.
I like very much both presentation. I want to put some question to the first one. I remember Hegel said that the humankind nothing invented till ancient Greeks till now, and this return to Platon for explaining what's happened now is very interesting. I remember, for example, when we describe the pixels in the computer, the theory of homeomeria of Anaxagoras. So Anaxagoras visualized how many thousand years ago what's happened on the screen of our computer now, recreating the world. In the same time, I like very much this debate between symmetry and movement. I remember the school from Elea and Parmenide versus Heraclit. So you see the ancient world, Greek world, had the meaning of the symmetry. Now I want to put three questions. First of all, I remember that Stephen Hawking himself, he described the black holes and the biography of the stars using the symmetry of the sphere. And the theory of unified fields is very interesting with this debate between symmetry and anti-symmetry. The first question is how the theory of unified fields could assume the symmetry or the anti-symmetry. This is the first one. The second one,
one after the one better, just to give time, for the speaker to reply, and then you can ask for the second one. Okay, so this is for
yeah, it's very short. The second is about the theory of completeness of Gödel, if there is an example of symmetry breaking. And the third one, I'm very interested to discuss a little bit about Feng Shui and anti-symmetric vision on Japanese Feng Shui. Thank you very much.
Okay, thanks very much. This is for Professor Mainzer, all of them. Okay.
Yes. And now I understood Hawking and Gödel. These are your questions. Yeah. First to Hawking. Yeah, by the way, I personally prefer Penrose, because Penrose was his brilliant mathematician, and he elaborated it in more details, not in the popular way of Hawking. And of course, both, and that is a tradition of modern cosmology and quantum physics, they are deeply rooted in the mathematical theory of symmetry. And the mathematical instrument nowadays is this group theory, which I mentioned in the beginning of my talk, these groups of self-mappings, that means automorphisms, very abstract, but very simple in a way. And the main idea is that the natural laws, what we call in a popular way, they are objective. They are independent of the perspective of a special observer. They are objective. That means mathematically they are invariant. But the question is, invariant to what? And by that distinction, we get these different modern theories in physics. for example, special relativity is also an objective theory, but here invariance is restricted to uniformly moving inertial systems, and they let the laws of electromagnetics in this case and mechanics invariant, and then you can go on step by step to all these other theories nowadays with different groups of transformation which characterize the invariance of these laws. That is the idea of symmetry mathematically. And all these well-known visible symmetries, intuitive symmetries, which we know from the antiquity and in arts, they are only examples in the visible world with invariance of forms and figures and so on. That is the main idea here. And then coming to Hawking, of course, this is a famous symmetry breaking, symmetry and anti-symmetry, of course. And so let me say, from a mathematical point of view, we have these tools, which I explained before, of group theory, automorphisms, and so on, to describe these theories. And that allows us to make precise predictions of the certain assumptions of symmetric theories. But then in the end, and that is the difference between physics and mathematics, then in the end, it must be decided by experience. So our nice theories of symmetry and asymmetry must be decided by experience. And that, of course, is an open discussion until today, how to explain the observed symmetry breaking of matter and antimatter today. We have the tools, but we have to wait for the decision of empirical research. Now, concerning Gödel, Gödel is also involved in the symmetry discussion, but in a tricky way. A main symmetry assumption of physics is the so-called symmetry principle, which assumed in cosmology that the structure of the so-called Hintergrundstrahlung, the microwave radiation, is homogeneous and isotropic. That means that in the world, in principle, no orientation and is distinguished, and no position is distinguished. That means homogeneity and isotropy. And that is a very strong assumption nowadays of symmetry of the world. And more or less, it is confirmed by the microwave background radiation today. And now coming to Gödel, Gödel considered a solution of the Einsteinian fields equation, which allows mathematically a universe where only homogeneity is confirmed and isotropy is violated. And so he came to a solution that was in the age of the 40s. He came to a mathematically possible solution that was very surprising for Einstein, by the way, these tricky guys there for mathematical logic, and namely that only homogeneity, that means a direction, is distinguished. And that leads him to the assumption of a circular trajectory and a movement popularly speaking, it is possible to travel in the past and mathematically possible, but as far as I know, it is more or less rejected nowadays by what I explained before, homogeneity and isotropy, which is more or less, at least in a statistical way, confirmed by modern observations of the universe. Now, that is Gödel and symmetry, and the first part was symmetry and
May I make a quick remark?
Antimatter, of course. Yeah.
May I make a quick remark?
Yes.
A quick remark. Your question specifically was about the incompleteness theorem.
Yes.
Just to complement what the president said, the solution of Gödel was very surprising. People didn't know that Gödel had an expertise in general relativity, but he did actually. Gödel published very little, as you know, but he knew a lot. So he did understand general theory of relativity, and that's why he made this contribution. However, actually, in this book, I mentioned ways of comprehending. I describe Gödel's main result with a completeness theory, and as far as I can see, there was no breaking symmetry involved.
No, it had nothing to do with symmetry. It has something to do. The Gödel result of incompleteness has something to do with the status of theories in general. You know, what he actually mathematically proved is that a theory, a mathematical theory, at a certain level of complexity, that means arithmetical theory with addition and multiplication must in principle be incomplete in the sense that it cannot be represented by a formal system. And that has consequences for computer science, of course, that in general you have undecidable series, and you have incomplete series which cannot be represented by formal programs for a computer. These are the consequences of this result of Gödel. But I think the other result of Gödel, because he was only a hobby physicist, that is also very interesting in order to underline the distinction between mathematics and between physics. Of course, the field equations of Einstein open a lot of mathematical consistent possibilities, but physical reality is different stuff.
Thank you very much. I saw that Willibald Plessas, he wanted also to, you have a hand raised.
Okay, I wanted to add some remarks to both speakers, namely regarding global and local symmetry transformations. So we see it best in physics, because there we can also formulate it strictly mathematically. So we understand the following. In the first instance, you have non-observables. With such non-observables, symmetry transformations are connected, because if you change an object by a transformation into another position, then it does, if it is not observable, you will realize a symmetry. Now with these symmetry transformations, as Klaus Mainzer said, we combine generators which generate these symmetry transformations. Now these generators are very important because they constitute constants of motion. So they constitute conserved quantities. And I think this is independent of any perception. This is, as far as we can understand, a mathematical concept which is generally valid. Now, with respect to local symmetry transformations, we can generate forces. And this is also what Mainzer mentioned. Namely, we have gauge, so-called gauge theories, which assume local symmetry transformations and thereby generate the forces that we know: electromagnetic, weak, strong, and maybe even gravitation, even though this is not yet understood. Now, with these local transformations, we have these gauge bosons, and the masses of the gauge bosons are explained or can be explained by the Higgs mechanism, but not in the standard model of particle physics, the masses of the constituents. So the masses of the constituents, which are, for instance, quarks and leptons and electrons and so forth, cannot be explained by the Higgs mechanism. They are just parameters now that are put into the standard model. And so this is what I stressed also in my talk, namely that we use global symmetry transformations to put particles, constituent particles, into a scheme that we can design into a certain texture. And we use local symmetry transformations to generate forces and therefore to create dynamics in the world. So this is, I think, most transparent in present-day physics, even though it cannot be carried through, as far as I understand, to all further fields, for instance, chemistry, life sciences, and even arts.
Yeah.
So this is what I wanted to add.
Yeah, thank you very much. Of course, I could not deepen it in detail because I had a so large program, but this point is absolutely essential, namely the transition from global to local symmetry. And you will have remarked, I like Plato, because he was also, because Plato liked mathematics and his mathematicians in those days, and had brilliant colleagues in Athens in those days. Now, so the idea that with this transition from global symmetry to local symmetry, something in the world comes into existence, exactly what you said, namely the forces which we observe, they are characterized by these gauge symmetries, and these are local symmetry. That is an unbelievable deep insight, I think, which is made precise by modern mathematics, but more than that, it is confirmed, at least in a restricted way for certain forces. It is empirically confirmed by our accelerators experiments. And that is very interesting. By the way, I like to mention one of these mathematicians who was involved in that. That was Hermann Weil.
The first one.
He was the first. He had, from a mathematical point of view,
of course,
a very Platonic way. In the early years of the 20th century, he had this idea. It was first classically formulated by him, but then it was open first to gravitativity theory, the idea that even the gravitational forces are introduced by the transition from a global symmetry, namely in special relativity, to a local symmetry in gravitation. The assumption of gravitation in that theory is a compensation of local deviation, which is initiated by accelerations. You know the main idea of general relativity of Einstein, namely the equivalence of acceleration and equivalently to that, the gravitation. And gravitational force as compensation of all these deviations of global symmetry, which emerge by local accelerations of, in this case, inertial systems. And this idea in classical physics later on was transported. That was also a first idea of Weil, but it was false in his first suggestion to quantum physics, and that was the step in the series which we discussed now of gauge fields in modern elementary physics.
Thank you. We are running out of time, so I would like to give the opportunity to other speakers. Dusan Shuput.
Thank you. I enjoyed both talks very much, and I will ask a few naive questions because I'm not a mathematician, I'm not a physicist, but a medical doctor. And talking about perception, you know, it was very interesting how you decompose an image of an object and then you compose it again. And there's a question for both of you, actually. Is the object that is constructed in our brain symmetrical to the one that we see or not? That's the one thing. The other thing is that we understand what we can somehow sense with our senses or measurements or whatever. So I think our world is not complete at all.
Our world is not complete?
It is not complete world because what we know is far less than probably exists.
Absolutely.
So if we go to the very, very beginning of the universe, I don't know how to say high numbers than femto or so, but in beginning, if you have particles that have no characteristics and then they get characteristics, and then you get symmetry and then you lose symmetry and you get something new. But isn't it symmetry so fundamental that maybe we have many universes? So things that are not symmetric in our world, asymmetric, maybe we have something going on right now in another universe we cannot comprehend, but it just may be symmetrical to what we see here. That's all. It's very naive, you know, but for me, it's still interesting. Thank you.
Maybe I can make some quick remarks. Not so much. No, first of all, I don't think the question is naive. The question has a starting point, which is absolutely well stated, namely that we are aware of much, much less than our brain perceives. And this is a fundamental point. You see, I always claim that our brain knows much, much more than we do. And this is the essence of it. The essence is that, as you know, evolution works in a very interesting way, solves continuously new problems through trial and error, and invents new solutions, but never throws away something which had used earlier. Early organisms were able to survive without being aware. At some point in evolution, and this is a long story, the first Big Bang took place. Namely, the brain informed itself of what the brain already knew, and we became aware. This process is both slow and incomplete. They're very, very, very well-defined experiments, the beginning by Libet, but now they have been improved, which show that this process from perception to awareness is quite slow. It's of the order of 1/3 of a second. So when I see your face, I have the illusion that I just saw you. No, my brain perceives you, but it will take, see, so when we see a cat and we break, we have the misconception, the illusion that we break because we saw the cat. No, we saw the cat in about 100 milliseconds. Our brain saw that. Our brain made the decision to break, and then a third of a second later, we became aware of the whole thing. So the first statement is that this process of awareness is very slow. The second statement is very, very incomplete. And there's a lot of discussion, but we don't have time to do it now. So of course, we perceive much less than our brain. But in addition to this, then you put another question of how much the brain is possible to perceive, and this is a different story. So there are two different sources of this incompleteness, if you like. One is how much our brain can perceive, and the second is how much we can become aware of what the brain perceives.
Okay.
Yeah, but Professor Dushan, so Dushan asked a different question. So he asked, is the object in the eye symmetrical to the one in nature? And I think this one can answer clearly.
No.
It is not. There's no symmetry transformation.
Of course not. Of course not. Of course not.
Okay, Klaus, would you like to add to this Dushan's question?
Yeah, I would, because we are now running in the end, emphasize concerning the connection between what we do in the natural sciences, especially in physics, in connection with the insight of modern cognitive sciences, and that is again a bridge to the arts too. I think a fascinating line is to explain in all these sciences what we mean by creativity, and I try to explain it with symmetry breaking. So there were already in all these steps in early universe and in the chemical emergence and in the emergence in the Darwinian evolution, and finally here in the human brain, there were these processes more or less randomly where novelities emerge, and now we observe this process in the brain. And I think that is the fundamental question nowadays. How can we explain these emergence of novelities, not only in the sense of structure emergence, but of structure recognition? Yeah,
thank you.
That was in the second. That was the case in the second talk.
Thank you.
And you know, last remark. You know, I'm also engaged, especially nowadays, in artificial intelligence. And so for me, the absolutely exciting question is, how far is that possible by machines, or is it reserved to us?
Thanks.
Maybe as a physician,
I think we have to shorten, the questions, because the questions become, lectures. So the time is, we are running out of time. So I would like to ask Professor Boudis if he has a question.
Bounties also, Tassos.
Yes, just a short remark that in the book I was reminded of, and I sent you a message about from Ian Stewart and Golubitsky. I was back in 1992. There, the concept of bifurcations that were so eloquently discussed by Professor Mainzer is into a sequence effect, where each bifurcation makes things more complicated. And so that's how we arrive at chaos. So this theory of chaos and all that you have heard and you know about is discussed very beautifully in this book as a sequence of infinitely many bifurcations. So this is one other aspect I wanted to bring up.
Yes. Good.
Thank you. Somebody else, Grote? Yes, you have to ask. You have rising hand. We cannot hear.
Yes.
Thank you. Okay.
You can hear me?
Yes, yes.
Okay. I'm sorry, but I cannot continue the scientific realms and aspects of this conversation because I'm engaged in an artistic realm. And so I have just a very simple question concerning Professor Mainzer and the idea of or the aspect of symmetries. So, and I would like to know, according to his opinion, which was more important for the development of mankind, the understanding the abstract principle of symmetry by our brain, or to perceive the principle of symmetry by our senses?
Mm-hmm.
Yeah, so it's a difficult question for a cognitive scientist. What was first, Of course, you know all these answers in epistemology. We all start, that is said by the famous epistemologists in modern times, from Locke to Kant and others. We start with our senses, and that is, of course, confirmed by modern cognitive scientists. But without the ordering conceptions, that would be not sufficient. Of course, the symmetry processes which I described in my examples with these alternating figures, is it a face or a vase and things like that, they are more or less unconscious. There are tiny awareness of details which are more or less unconscious, and there are a lot of empirical inquiries about that, and they decide in the end the emergence of the dominating figure, the vase or the face in this example. But if you go to other examples of symmetry breaking in the brain, then you need, for example, in physics or so, then you need these tools, these conscious abstract tools, in order to explain these processes. So I think both approaches are in the end necessary, and that is, of course, important for applications of an artist too.
Thank you. I would like to ask Klaus, follow up, this discussion, something to you, which is related, I think, with the inverse perception that Fokas said later. In the spontaneous symmetry, breaking process, the determination which branch of bifurcation, as Tassos before said, is taken for an outside observer unaware of the fluctuation, the choice will appear arbitrary. But in the cognitive issue that you mentioned of symmetry, how is this breaking point could connect with the sensory input of our perception?
Absolutely.
Yeah. Can you hear me?
But was for me or for?
Yeah, for Klaus.
That's what I thought. Yes, yeah, that's what I thought.
For me, what was your point?
You are talking about spontaneous symmetry, like the Big Bang, for example, an observer, and we have the bifurcation, the decision, what will happen, in this, and for an outside observer, which is unaware of these fluctuations that will happen, the choice will appear somehow arbitrary, as chaos, as somebody said before. But in the cognitive issue of symmetry that you mentioned, how is this breaking point would connect with the sensory input of our perception?
Yes, that depends, of course, on the considered example. And so symmetry breaking in an abstract way is not sufficient. You need the concrete mechanism in the field you analyze. For example, in the physical case we discussed, there was this Higgs mechanism, but the Higgs mechanism is not able to explain the bifurcating trees in the chemical or in the biological evolution. So there new mechanisms came in, which were discovered by science. For example, in the Darwinian evolution, that is, of course, the random fluctuations of mutation, which explain the bifurcating points and the driving forces in this case. And in the case of the brain, you have also different mechanisms which are nowadays explained by neurological mechanisms, which can, in the end, or are in the end simulated even on computers. And that is the case which I mentioned with these symmetry breaking alternatives and other processes. So in the end, it depends on the concrete field of application. Different mechanisms, but from a mathematical point of view, these are all examples of assumed symmetries which are broken at critical points. And the critical points are interpreted in biological, chemical, physical contexts.
Okay, somebody would like to say something on this?
Yes, I think one must be very careful, one must distinguish. So Darwin's evolution in biology is just a description, but not an explanation of the direction of biology.
Absolutely.
So we do not know the dynamics which drives the evolution, contrary to physics. So in physics, we know from several interactions that are existent, for instance, electromagnetic interaction. We know the dynamics, how it is generated, how it originates, contrary to any other science, I think, in particular biology.
Yeah, you are right, but a short comment to that. You are quite right. The historical Darwinian description of his bifurcating tree is not on the same level like the bifurcation tree of modern standard theory. That is obvious. But nowadays, now from a physical point of view, in the context of thermodynamics, we have tools now to explain the bifurcation trees in a physical way. For me, that is also my research in that field. For me, these bifurcation trees in biology are more or less an example of what is described in thermodynamics. In thermodynamics, in the non-equilibrium, nonlinear thermodynamics, we describe also bifurcation trees. You know, the thermodynamical phase transitions of first and second order, and they explain in a physical way, the emergence of new structures. And that is my point here, that may be the background to explain in the biological evolution too. It is at least the physical framework.
No, but I would agree with Dr. Plessis that there's a huge difference between right now what is called theory, the Darwinian evolution theory, which is more and more is accepted that it's not a theory, just a framework in which you can study things. For example, since 2000, we have this new discovery of horizontal gene transfer, which replaces these bifurcation structures with a completely different structure. So, for example, it is nowadays more or less impossible to study the history of genes. Such a thing doesn't exist. How do bacteria survive? Bacteria survive not by mutations. Bacteria survive but with horizontal gene transfer, which is a huge mechanism never suspected by Darwin. So this is again, I always consider the Darwinian theory as a framework, but now it's become more and more clear that it's a very, very incomplete framework. And if you like to say it even more roughly, if I wanted to convince people that God exists, I would use as an example physics. Because there you have very concrete, very well-defined laws which are expressed in a beautiful way through mathematical process. In biology, it doesn't seem right now that, and maybe this is why the role of mathematics in biology cannot be as fundamental as the role of mathematics in physics.
If
you look at quantization, what happens? I mean, you go from classical to quantum mechanics not by discovering new physics, but by mathematizing. This is the ultimate apotheosis of mathematics. I don't think something like that, at least so far, it's inconceivable that something like that happens in biology, because evolution works by trial and error. We have been used through the reductive approach of physics to try and reduce everything to some fundamental principles. I don't think, although there are some general principles that dictate the evolution in biology, local problems are solved in a local way. And this is the difficulty of artificial intelligence, to mimic the brain and various other processes. It is, the approach is too generic, while evolution solves the problem ingeniously, locally, after huge number of trial and errors, since it had billions of years to do this.
Yes, you are quite right. Biology is more or less only a phenomenological theory, the Darwinian theory, but the point is, modern physics is not only quantum mechanics and not only relativity theory, but we have nowadays in physics the tools in, I mentioned it again, in modern non-equilibrium dynamics, thermodynamical processes, to describe it in a mathematical, precise way. And the chaos theory, which was mentioned before, can be embedded in these kind of theories. And there you have bifurcation processes again. And in this bifurcation processes, in these phase transitions of stochastic differential equations, you can explain the emergence of new structures. And that in the end, I strongly believe that point, that in the end will be the framework to explain from a mathematical point of view, with the same level, like the cosmic processes, the processes in biological evolution. Of course,
I strongly doubt it. I strongly doubt it.
I think
that will be the framework.
I think we have to make a special, workshop on these two lectures.
Yes, this is what I wanted to suggest.
I will organize. Any questions for Professor Fokas?
I would like to make a short remark.
Yes.
It's also a reaction to Adalbert Grote commentary. I would like just to mention that the music of Bela Bartok, the Hungarian famous composer of the 20th century, was analyzed by a Hungarian musicologist, Lendvai. And he demonstrated that the music of Bartok is following the rule of Sectio Aurea. And this is an incredible way of trying to understand the process between this continuum you spoke about, unconscious and conscious processes, because it is indeed, if we look at the analysis of Lendvai, it is possible to demonstrate that Bartok used this theory without knowing about it.
Of course.
With intuition, and it's not only once, not in only one dimension, but it's at the same time shifting processing of Sectio Aurea on different level of music structures. So
this is a very beautiful remark
with our subconscious.
Very beautiful remark. And since the president mentioned earlier the question of creativity, in my opinion, it is impossible to discuss creativity without understanding the processes that take place in the unconscious, and great personalities, from Schoenberg, that also was mentioned, to Einstein. I'm flabbergasted that they used exactly the same. I'm sorry, Schoenberg and Picasso use exactly the same statement
but they
describe.
Consciously, Bartok didn't use it constantly. And
Understand.
Talk about Sectio Aurea also as it's
of course, creativity.
Perfect projection of Sectio Aurea.
You see, in my opinion, the more creative a person is, the greater the input of the unconscious. And for Schoenberg and Picasso, these statements were made absolutely explicit. They use more or less the same terminology. You see, for example, Schoenberg writes that a composer would like to discover a posteriori the laws that dictate his music, which he perceived as a dream. What a better way to express the effect of unconscious process, but as a dream. And Picasso speaks similarly, how he tried to take pictures when he was creating his paintings in order to capture this dream process. And it is fascinating. And just a last remark, I love opera, you see. Yeah. And people, of course, you sometimes ask, how can you compare Verdi and Wagner, for example, the two most, and I believe that the difference, but it's a different discussion, the difference is that Wagner was much more free from his conscious world than Verdi was.
You're absolutely right. But if we make analysis of the music of Wagner, you don't discover this element I spoke about it by Bartók. If we remember, Emmanuel Amiot spoke about Beethoven and demonstrated in the Durchführung of the ninth symphony, or such an incredible process which may be explained mathematically. And Bartók, as I repeat, didn't make any calculation. Schoenberg knew exactly that he has to work with intervals in different dimensions, so he could do it consciously, but Bartók did it.
But you know, with Tassos,
consciously, yes.
One last remark: with Tassos, we wrote a paper together where we analyze the fractal aspects of Mondrian. I mean, Mondrian used fractality like Pollock used fractality well before Malbrook discovered it. So this is the incredible creativity of unconscious processes.
A question for Thanasis.
All these nice remarks underline the importance of our lecture series, because some people believe that only in antiquity, the Pythagorean tradition, then music was a part of the exact sciences in the theory of, the sense of the theory of proportionality. But nowadays, all these examples illustrated, more or less conscious or unconscious, there is a deep connection of creativity processes in music, in arts, in painting, and in the so-called exact sciences. And this very
question for Fokas. I would like to know. I didn't hear the. Thanasis, probably I didn't got the point of Fechner's, Fechner in 1960 about who has spoken about the percept is completely determined by the sensory input. I don't know, probably his approach, has been overwhelmed by others. But I would like to ask you if you could clearly somehow make the distinction between visual space and material space, and if the comprehension of these two have an impact, it may have an impact on the structure of phenomenal space, and or I could say multiple dimensions in the time-space domain.
You see, this is too difficult question for me. Remember that Piaget, you know why Piaget studied the psychology of children? See, do you know why? Because Einstein asked him the question of do children have the intuitive understanding of space that we do? Because he wanted to more or less answer your question. So Piaget became very famous. I mean, if you look at his book, he writes that he owes this line of investigation to the question asked by Albert Einstein. I don't think I'm ready to address this question.
And the correlation, you have, I think, worked on this mental time travel, if I remember.
But I think your question is, from one point of view, rather simple, because it is the same process. On the one hand, and that is inquired by physics, we have pattern formation in nature. New structures emerge. That's the one side. The other side is pattern recognition, pattern formation, pattern recognition. And pattern recognition, that is analyzed nowadays by cognitive sciences and in the end also by artificial intelligence. How are there artificial systems which are able to recognize what you call the visible world? But it is the same, this two sides of the same medal, I think, namely the emergence of structure in the world recognized by the human mind. And so
I have, you see, I have to leave in a few minutes, but just, I mean, if you remember, another aspect of local versus global is this Gestalt approach. You see, Gestalt started from this group in Germany that addressed precisely how the brain perceives form, how the brain goes beyond local and see global. So this is related to pattern recognition, and we understand quite a lot about this subject, but this is a different process. You see, if you give, for example, to schizophrenic an age, we have a doctor, so he can confirm this. If you give to a patient suffering from schizophrenia an H letter, which is formed by little circles, and ask this patient to what he sees, they will see the little circles. They're not all, they emphasize the local, not the global. You see, and they remarkably didn't know that until recently. The first Gestalt experiments were similar, but people, of course, saw the form. Gestalt means form. So the brain has this interplay between local and global, not the local symmetries in terms of gauge symmetries versus global symmetries, but it's local versus global in the sense that I mentioned how a percept is broken into local constituents like orientation, color, and movement before the global, the synthesis is achieved. And the brain does this all the time in a way that allows the brain to perceive structures, patterns, etc. You see, okay. But with respect to artificial intelligence, since this sort of challenge, you see, the brain has tremendously important characteristics which are not present in artificial intelligence. Okay. One of the most obvious, but also already the president mentioned this limitation from the incompleteness theorem, but another even more obvious statement which has been neglected is that the brain is embodied. Oh yes, it's obvious, it is obvious, but the fact that the brain is embodied has huge implications of how we think through the action of hormones, etc., etc. So it is enormously difficult to replicate this in artificial intelligence.
Thank you very much.
Look, excuse me, I have a question. You are Ioannis Vetra. To every, it was understood that
I think that we are not going to finish. You know, I think as I proposed, you allow me to make a special workshop between our class, including class medicine. Dusan is here. A workshop, not a colloquium, a workshop with these issues. I will.
That's excellent because brain is now we know a lot, and it's very good to compare.
So it will be class of medicine as well. Okay.
Okay.
We have a little question here, Ioannis Vetra. It was understood that elements obtained.
Okay, the last question.
Ioannis. Last minute. What equal elements are used to create images in the imagination in dreams, especially when there are scenes never seen before in life?
No. That's a very good question. Maybe I can quickly answer this. You see, now it is possible for me to explain the majority of my dreams, you see? And this is very simple. So what happens is the brain continuously makes associations, you see? So you tell me a story which has to do, let's say, with music. My brain makes immediately this association with a particular opera that I have never seen, but doesn't matter. I have imagined, I have thought about this, and then this particular neural circuit is excited, and in the evening you watch, you become aware of this. So dreams as a result of excitation of particular neural circuits that are excited because during your awake state there was excitation of a similar or associated neural circuit. This is the most reasonable explanation for what dreams are and how.
Short remark, short answer from my actual research. Now I'm more engaged in artificial intelligence and things like that. So the question actually is, in modern AI, in modern machine learning, are these systems able to dream? Is a computer able to dream? Yes, in a certain circum-understanding, it is. In the case of machine learning. But that would be also a topic for a new discussion round, as you announced it. And I think that is a revolutionary challenge now to confront the researchers in cognitive science, especially in dreaming and things like that, in emotions, in feelings, with that what is going on in modern machine learning.
Or the other way around, the modern machine learning.
My personal belief
or the other way around, the modern machine learning have to understand how the brain works in order to have any possibility to mimic it. It's impossible. It's impossible for the artificial intelligence to model dreaming without deep understanding of what the physiological mechanisms that give rise to dreaming. In the same way that I disagree with the approach which tries to use mathematics to explain how the brain works, contrast to trying to understand how mathematics emerges from the way that the brain functions.
We will need new steps in the AI, because in AI we have nowadays the situation in machine learning that all these successes nowadays are only possible by a mass of data, big data. And then we have these nice fast algorithms to solve the problems in a statistical way. But the main ability of the human brain is, and Einstein, by the way, is an example. He had only very few data in 1915 and in 1905, and he had this brilliant idea, human creativity, and to achieve a theory like general relativity, which has nearly no confirmation in his time, but then step by step it was confirmed. It is a brilliant theory until today of our universe with very few data, and that with the modern AI cannot be explained. So that needs new insight.
Thank you everybody for this fascinating, illuminating talk. That was the only, I think, Violeta, this is the only, I think, colloquium that happened, this hot discussion and enthusiasm, and great interest. Thanks very much for the two speakers, especially for the participants and those who have the patience to remain up to this moment. And we thank you, and we look forward for our next.
Many thanks for organizing things. I'm deeply grateful. Thank you very much.
It was very inspiring.
Thank you very much.
Bye-bye.
Very exciting.
Thank you.
Good evening. Nice weekend.
Bye bye everyone. Thank you very much. Thank you.